At D, lots of flux coming out of the board. At E, nothing. So what's it going to do? It's going to try to get back to where it was. It's going to try to add flux coming out of the board. Right? It always opposes the change. The change was a reduction in flux, so it's going to add to it to try to get it back to a big flux. So it has to go counterclockwise to get the flux out of the page. You okay with that? And E to F starts out with no flux, ends with no flux, never changes. No change means no generated current. Okay, did that help a little bit? Okay, let me show you, let me go back to our, we use this a lot, the rails. The bar, external magnetic field. And what we're going to do is move the bar, doesn't matter, to the right. We're going to call this, what do you want to call this? X. And we're going to call this W or L. So L is the length of our bar. X is the distance over. All right, so we want to know what's the induced. If we move the bar at some speed V, we're trying to figure out, we know the R, the resistance in the wire. We know the speed we're moving our bar. We know the magnetic field. We're trying to figure out what the current is. We know the direction of the current, right? What direction is the current? Counterclockwise, right? Because the flux is increasing into the board, so a current gets set up to decrease it, to counteract the change, right? It has to be counterclockwise. Down through the resistor, up through the rod, right? Counterclockwise. Okay, so we know all of that, but we don't know the magnitude of I. So we're going to use Faraday's law. The induced EMF is equal to the number of turns, change in flux, over change in time. And all I care about is the magnitude, because what I'm going to do, I'm going to change this circuit into this one. Right, moving that bar to the right causes current to flow. It acts like a source of EMF, like a battery. So I'm saying this circuit is equivalent to that one if I get that value of EMF right. If I get the right value, I can make an equivalent circuit, and I know how to analyze a simple circuit like that, right? I can figure out what the current is. If I know the potential on the battery and the resistance, I can figure out what the current is. So let's look at this. N is 1. The flux is equal to the magnetic field times the area. And the area is going to be L times X, right? This is going to be my initial flux. And my final flux is going to be BL X plus delta X. Right, because it's changed by some delta X in some time delta T. We good with that? And so what is my induced EMF? It's going to be just number of turns times the final flux minus the initial flux all over the change in time. And what is that? That is just going to be B times L times delta X over delta T. And what is delta X over delta T? How much does this thing move in a given amount of time? Velocity. This is another reason why it's nice to use this script E for EMF instead of V for potential, for voltage. Because we have a lot of velocities in our equations. You'd have a lowercase v for velocity and a capital V for potential. So this is a better symbol to use here, the script E. It's the same as our capital V that we've been using for potential difference, right? It's an induced EMF potential difference. Okay, so the potential difference here that's generated is just the magnetic field times the length of the bar times the velocity of the bar. And if we knew those three things, we could come up with a value, plug it in for E, and then for the battery, and then figure out what the current is. So I is just E over R. Okay. So sometimes you're told, you know, something is changing, a magnetic field is changing by this much in a certain amount of time. You can use this equation and change in flux over change in time, figure out what the induced EMF is, and then just replace it with the battery with that EMF value and solve for the current or whatever they're asking for. All right, we'll pick it up again next time.